Section 1 Introduction. Let's delve into the concept of grokking in the context of deep learning. Grokking refers to the process where understanding or generalization occurs after memorization. This phenomenon is intriguing and challenges our comprehension of deep learning. Several explanations have been proposed for grokking, many of which revolve around the idea that grokking is essentially a form of compression. The idea is that there are two types of solutions: a memorization solution and a generalization solution. The memorization solution is easier to learn and is therefore learned first. However, the generalization solution is more efficient and thus emerges later. Various metrics have been suggested to characterize this process of compression, such as L2, Fourier gap, and network efficiency. However, none of these metrics provide a clear interpretation in terms of information or computational complexity. We propose a new metric called the linear mapping number, LMN, which measures the complexity of a network or a subnetwork. In essence, LMN is an extended version of the linear region number for ReLU, rectified linear unit, networks. ReLU networks are known to represent piecewise linear functions. They divide the input space into regions where the network behaves as a local linear mapping. Different regions have different linear mappings. You can think of ReLU networks as origami, folding a flat input space into complex shapes. The number of linear regions measures the network complexity. LMN extends the concept of linear region number to networks with smooth activations. We argue that LMN is a better metric than L2 for measuring network complexity in deep learning, especially for grokking. For instance, consider linear networks, which can only represent linear mappings even when they are deep. For such networks, LMN always gives 1, but L2 can be arbitrary and hence not very informative. Moreover, LMN can be naturally interpreted as information. If you want to compress a network into linear mappings that depend on the input, then the compressed information is essentially the LMN times the size of one linear mapping. We use LMN to characterize the compression process of grokking on three algorithmic tasks: modular addition, permutation group S4, and multi-digit XOR. After memorization and before generalization, the LMN decreases steadily and has a strong linear relation with test loss. In contrast, L2 is correlated with test losses in a complicated nonlinear way. For modular addition and permutation, the LMN starts to level off after grokking, as expected. For multi-digit XOR, LMN shows an unexpected double descent after grokking. This reveals something intriguing about the XOR case, which has two generalization solutions that are almost degenerate, so the network jumps between these two solutions. The paper is organized as follows. We define the linear mapping number, LMN, in one section. In another section, we use LMN to explain grokking, showing that it is related to L2 but also better than L2 in several senses. We discuss related works in another section. The linear mapping number, LMN, is a generalization of the linear region number for ReLU networks. For simplicity, let's first consider ReLU networks. A ReLU network divides the input space into linear regions. In each region, the ReLU network behaves like a local linear mapping, although different linear regions correspond to different linear mappings. The number of linear regions has been proposed to measure network complexity for ReLU networks. While the linear region number is only defined for networks with ReLU activations, our proposed linear mapping number is defined for networks with any activations, including smooth ones. However, ReLU networks point to a route for how to define LMN generally. If two samples lie in the same or different linear regions, a straight line connecting them in input space will remain linear or become nonlinear in output space. This inspires us to measure the linear connectivity between two samples. The more linear the output line is, the larger the linear connectivity is. For a network F mapping from AD one-dimensional space to AD two-dimensional space, and two input samples Xi and Xj in the D one-dimensional space, we denote the linear connectivity of them as liege. We interpolate linearly between Xi and Xj in input space, which corresponds to the output curve Yiege. The kth dimension Iki is simply a scalar function of lambda, so we can evaluate its linearity by doing linear regression and calculating R2, the square of the Pearson correlation coefficient. We define liege as the average of R2 over dimensions k. Note that liege is between 0 and 1. The R2 is measured using uniform points on lambda between 0 and 1. When YEJ is a straight line, LEJ equals 1. When YEJ resembles a symmetric parabola, LEJ equals 0. We define self-connectivity LE as 1. In summary, a larger LEJ means that the network behaves more like a linear mapping for sample I and j, while a smaller LEJ means the network behaves non-linearly in between sample I and j. We can stack LEJ into a matrix L such that LEJ equals LEJ, and call L the linear connectivity matrix. If we say linearly connected samples belong to the same linear mapping, then the problem of counting linear mappings boils down to the problem of clustering. Given the sample similarity matrix L, how many clusters are there? Since the number of clusters is a discrete quantity and determining it may be non-robust or hyperparameter dependent, we use a soft estimator leveraging the eigenvalue structure of the similarity matrix inspired by von Neumann entropy. We define the eigenvalues of L as lambda underscore I. Note that L is symmetric, hence all eigenvalues are real. L is almost semi-positive definite, i.e., all large eigenvalues are positive, but there might be a few small negative eigenvalues, which we take their absolute values. We define normalized eigenvalues as tilde underscore lambda underscore I equals the absolute value of lambda underscore I divided by the sum of the absolute values of all lambdas. Then we treat the normalized eigenvalue vector as a probability distribution. We define the nonlinear complexity of the distribution, measured in bits, as SNL and define the number of linear mappings LMN as 2 to the power of SNL. Note that given a dataset sheet, the quantity SNL defines a measure of the nonlinear complexity of any function, regardless of whether it is defined as a neural network or not, and that SNL equals 0 for any linear or affine function. To get some intuition of the definition above, let's consider a case where there are C clusters with each cluster having the equal size n, C, and samples are perfectly linearly connected to other samples within the cluster. In this case, L is a block diagonal matrix with C blocks, each block being an all-one matrix. The normalized eigenvalue vector is then tilde underscore lambda underscore I equals 1, C for I less than or equal to C, and tilde underscore lambda underscore I equals 0 for I greater than century. Its entropy is S equals log C, resulting in LMN equals C, as expected. Note that LMN does not only apply to the whole network, but also to any subnetwork. In particular, LMN between an intermediate layer and the output layer is of interest. Section summary. The phenomenon of Grokking, where generalization occurs long after memorization in deep learning, is challenging to understand. This paper proposes a metric called linear mapping number, LMN, to measure the complexity of a network and characterizes the compression process of Grokking on various algorithmic tasks. LMN is a better metric than L2 for measuring network complexity, especially for Grokking, and it can be interpreted as the amount of compressed information in a network. Section 3. Using LMN to explain Grokking. In this section, we'll discuss how we can use LMN, linear mapping number, to understand the process of Grokking, which is the ability of a network to generalize after overfitting. We'll demonstrate how LMN can help us understand the process of network complexity reduction that occurs before Grokking. We'll see that LMN consistently decreases from the point of memorization to the point of generalization. To do this, we set up an experiment where we trained 3-layer fully connected networks with CLU activations to perform certain algorithmic tasks. These tasks included adding numbers modulo 31, composing permutations on S4, and performing a 5-digit bitwise XOR operation. We trained the neural network parameters using the Atom W optimizer with a learning rate of 0.001 and a weight decay of 0.2. We did this for 20,000 steps, using cross-entropy loss. The dimensions of the embedding, hidden, and output layers were 32, 100, and 31, 24, 32, respectively. We split all possible inputs into an 80-to-20 train test ratio. We measured LMN between the first hidden layer and the output logit layer, as the first hidden layer is the most significant in a 3-layer network. We plotted the LMN and losses during the training course for the 3 tasks. We defined the period before training accuracy reaches 100% as the memorizing phase, the period after that but before testing accuracy reaches 100% as the generalizing phase, and the remaining period as the finalizing phase. We observed that LMN decreases during the generalizing phase, indicating the network's underlying compression process. Interestingly, LMN showed a stronger linear correlation than the test loss when compared to the L2 norm of the model parameters. In the 5-digit bitwise XOR task, we noticed an interesting phenomenon. During the finalizing phase, the LMN briefly increased after generalization before decreasing again, forming a double descent-like shape. We think this could be due to two possible ways of handling individual bits. One way is to create a mapping for all 4 possible pairs of bits, and the other is to reduce the number of pairs to 3 by treating 0, 1, and 1, 0 identically. The latter is more efficient, but the former might produce better results earlier in the finalizing phase. We believe that the increase in LMN after generalization could be the model handling asymmetries by adding separate treatments for 0, 1, and 1, 0 pairs, and only favoring the more symmetric treatment afterwards. Grokking is a phenomenon where generalization occurs long after overfitting. There have been attempts to understand grokking by studying simple models, defining measures to characterize the dynamics, and linking it to double descent and optimization. Our work contributes to this understanding by studying grokking from a computational information complexity perspective. We propose a number of complexity measures to understand why deep learning generalizes. We extend the linear region number, which measures the complexity of ReLU networks, to the linear mapping number, which can accommodate general networks with any activation. We believe that the perspectives of information and compression are key to solving the generalization puzzles of deep learning, and our proposed LMN could be a useful metric in this regard. We plan to test the usability of LMN on a wide range of tasks and architectures in the future.